Here are two quick examples of applications of limits, both of which we will study in more depth in this course. The first example is finding the area underneath a curve defined by the graph of a function. So for example, right here I have a function, and I would like to find the area of this region underneath the function. How do I calculate that? Well, the idea is to use a simple shape that I already understand well, like a rectangle. I can approximate the total area under that curve with the total area of a bunch of rectangles. I know how to compute the areas of rectangles easily. And notice that in this picture, the rectangles we've chosen give a slight overestimate for the area. That's okay. In order to get a better approximation, all I have to do is use more rectangles. And as I use more and more rectangles, notice that the widths are getting closer to 0. So in order to find the exact area under this curve, what I really need to be able to answer is the following question. What will the total area of the rectangles approach as the width of the rectangles gets closer to 0? That's exactly the kind of question limits are designed to answer. Here's another application. Finding the slope of a tangent line. Imagine we have this blue curve, and I want to find the slope of a tangent line at this point. In this case, the tangent line would only touch the graph at one point. And if I want to find the slope, I really normally need 2 points in order to use the slope formula we learned in algebra. So we find another point on the curve and evaluate the slope of the line that connects those 2 points. Now notice, that's not going to be the slope of a tangent line, but if these 2 points are close together, then it ought to be close to the slope of the tangent line. How can I do better? Well, I use a point that's closer, or closer, or closer. Now notice how I wanted to find the slope of the tangent line here. Now I'm using another point that's very close on the curve in order to find the slope of a line that goes through both of them. And the slope of this line ought to be pretty close to the slope of the actual tangent line. To get the exact slope of the tangent line, what I need to do is ask, what will the slopes approach as I let these points get closer and closer to each other, as I let the distance between them get closer and closer to 0? Again, that's exactly the idea that a limit helps us express.